As we continue with our discussion on gas behavior, we're going to focus in on a very important theory called the kinetic molecular theory, and it's abbreviated KMT. It basically explains gas behaviors based on the motions of the molecules. It's based on an ideal gas, and an ideal gas is an imaginary gas that's going to follow certain criteria. We'll see that criteria on the next page. The first criteria of KMT is that gases are made up of atoms or molecules that are in constant, rapid, random, chaotic motion. Molecules are moving everywhere at extremely high speeds. The second assumption is that the temperature of a gas is proportional to the average kinetic energy of the particles. The temperature in Kelvin scale is proportional to the average kinetic energy of the particles. So if we double the Kelvin temperature, as we go from 100 to 200 Kelvin, we would double the average kinetic energy, the energy of motion of the particles. The third assumption is that gas particles are not attracted nor repelled from one another. And you'll notice that this is in bold-faced print, because we know in the real world gas particles do attract and repel other gas particles. The fourth assumption is that all gas particles will collide in perfectly elastic collisions. And basically what that means is when they collide with their container wall, all they're going to do is transfer their kinetic energy from one particle to the wall. If they're colliding with other particles, they'll transfer their kinetic energy from one particle to the next particle and so forth, so that the kinetic energy is not lost within the system, it just keeps on transferring. And the fifth assumption is that the volume of gas particles is so small compared to the space between the particles that the volume of the particle itself, the gas, is going to be insignificant. Basically what this is saying is that gases do not have any volume. They don't take up space. Notice this is also in bold-faced print, meaning that in the real world, real gases do take up space. We know that if we blow up a balloon, the balloon will inflate because of the air molecules that we're putting into the balloon. So the KMT is based on an imaginary ideal gas. What's a real gas then? Well, a real gas, like nitrogen or oxygen gas, will eventually condense into a liquid if we let the temperature get too low or we put too much pressure on that gas. And that's because of assumption number 3 and 5, that there are attractive and repulsive forces between gas particles, and gas particles do take up space. So real gases can deviate or change from ideal gas behavior when we're at high pressure. At high pressure, we're pushing on those molecules to get closer and closer together. We're compressing them. That's making the volume more significant than if they were spread out. So when we compare the volume of the gas particle to that more compressed, condensed space, it's a more significant volume. If you look at this illustration, you will notice off to the left that we have a single gas particle in a certain amount of space, and you can see that they have deemed this as low pressure. And that particle, in comparison to this amount of space, is very small. So they say that volume of gas is negligible, or gases do not take up any space, they don't have any volume. But if we put some pressure on that gas, we compress it so that there's a smaller volume. Now this gas particle actually is more important. It's taking up a more significant amount of space here. And so that's one of the reasons why real gases will start to deviate from ideal gas behavior at that higher pressure. Real gases also deviate from ideal gas behavior when we're at low temperatures. Remember what temperature is? It's the measure of the average kinetic energy of the gas particles. At lower kinetic energy, the molecules are moving slower. So that means the attractive forces that are between those real gas particles are actually going to take effect. They're going to start to draw the molecules closer together and condense them into that liquid state. The third factor that causes real gases to deviate from ideal gas behavior is one that you're probably not going to understand just yet, because we really haven't discussed the polarity of a molecule, but polar gases like hydrochloric acid will deviate more than non-polar gases like helium or hydrogen. And that's because polar gas, or anything that is polar molecules have charged ends, and charged ends attract other charged ends, and that affects the attractive forces, whereas nonpolar molecules don't have charged ends. We'll talk more about this one when we get to geometry and the polarity of covalent molecules. You can see at lower temperature that these gas molecules are moving at a slower pace, which means there's going to be more attractions between the particles. This real gas will not exhibit ideal gas behavior. The last thing that we need to talk about is how a gas moves. It can move through a process of effusion or diffusion. Effusion is simply when a gas escapes from a tiny hole in a container. You can see with this balloon that there are holes. Those holes are pores, and over time the air or the helium that is in that balloon will move through to the outside, and that will cause a smaller balloon after a certain period of time. The second way is diffusion. And diffusion is just that spontaneous movement of a gas moving from high concentration to low concentration until it reaches an equilibrium, until those molecules are equally spread apart. We can smell perfume that somebody has sprayed on them through the process of diffusion. As the perfume molecules are vaporized into the air, they will travel from their high concentration to obviously areas of lower concentration, and that's where your nose will then find those molecules and be able to detect that smell. Now, particle size does have an effect on effusion and diffusion rates. As the particle's mass increases, the particles will actually move slower. And so that means it's going to take them more time to get to their final destination. And usually that would be an area of lower concentration. So as the mass of particles increase, then the rate of effusion and diffusion is lowered. So if we take a look at this last diagram, you will see that there are two gas molecules that we're going to compare. The first one is hydrogen, which has a molar mass of about 2 grams per mole, and carbon dioxide gas, which has a molar mass of about 44 grams per mole. If we were to vaporize both of these gases into the air at the same time, we would find that it's going to take longer for the carbon dioxide to get to the nose than it would the hydrogen. Remember that the hydrogen molecules are really small. Smaller particles are going to move faster. They're going to move in rapid, random, chaotic motion, and they will find the nose very quickly. Whereas the carbon dioxide gas, which is actually odorless, so the nose is actually not going to smell it, but if we were just to kind of compare it, once again, it's going to move in rapid, random motion, but it's going to move at a slower rate because of the heavier molecules.